Hey guys, welcome to another lesson. So today we continue on and actually conclude the combinatorics or Perms and Combs topic by doing the pigeonhole principle. Now, for those that haven't done the principle before, it's not the easiest part, can be confusing, but what you'll find is a number of questions, once you sort of apply the framework, is actually not that bad, right? Now, for those that know, the pigeonhole principle did not exist before the syllabus was changed 3 years ago. So if you look at past papers beyond that, you will not find anything to do with the principle, any questions to do with the principle. You will find permutations and combination questions, but not the principle. So if you want to really look at the past papers that have these questions, 2020 onwards is where you'll find them. So guys, if you haven't already done so, please like the video if you can, subscribe to the channel, tell your friends. All right, let's start with the framework. Now, so there's a number of definitions for the pigeonhole principle that you can find in textbooks, on the internet. This is my sort of condensed version, and I sort of split it into two because the first one sort of demonstrates pigeonhole principle in its simplest form. And let me just talk about it, right? This one's saying, if I have n or more pigeons to be placed in n pigeonholes. Now, what that really means is that if I have n, let's say for simplicity, 4 items, right, or 4 pigeons, right, and I'm placing them in 3 buckets or 3 pigeonholes. Simplest term now, it's simple because there's only one layer, right, to be put in first, right? So in this case, the pigeonhole principle says that at least one pigeonhole will contain at least 2 pigeons. What that means is that if I spread the first layer, right, and I allocate them to each bucket or to each pigeonhole, then the remaining one, the remaining item here, right, has to go somewhere, right? And by placing it into any one of the boxes, then the pigeonhole principle is prove that at least one hole or at least one pigeonhole contains at least 2 pigeons. Now, theoretically, I could have placed all the pigeons into one hole, but then the pigeonhole principle will still be true, right? Because at least one pigeonhole contains at least 2. So the principle is mainly the layer spreads as much as you can, and then the remainder has to go somewhere, and that demonstrates the principle. Now, what does this generalized form look like? It basically says if I have m times n pigeons to be placed in n pigeonholes. Now, the way it works here is if I have 3 pigeonholes, this basically works on a general principle where what if I had sort of multiple layer of the pigeonhole plus 1? Then you can see there, what I can do is place 3 into the first hole, 3 into the second hole, 3 into the third hole, and then have 1 left over. So the principle basically says then at least one hole will contain at least m plus 1. M in this case is like 3, right? So m plus 1, which is 4 pigeonhole, which is exactly what that's saying. So the general principle allows for the fact that there can be multiple layers, right, of pigeons. That's important for later when they say, for example, give us 16 numbers divided by 3, how many in each remainder? Those type of questions really work for this. So most of the questions you'll see actually works on the general principle and not the first one. But the first one is good for simplicity, right? Just to show you how the principle works. Guys, that's enough of me talking. Let's attack some past papers, right? Now, you will also find that in a lot of the past papers in 3-unit Extension 1 Maths, the pigeonhole principle questions are in the multiple choice section. That makes sense because a lot of the times, there's 2 types of questions, by the way, for pigeonhole principle. You either apply the principle to find the number of things, or you apply the principle to prove that the number they gave you is the one that it fits within the principle, right? So one's like finding and one's proving. Whenever it's in a multiple choice, obviously it's a finding question, right? So let's start here. Private institution course regulation requires that the same number of students achieve each grade from A to E where possible. What is the smallest number of students required to ensure at least one particular grade is awarded 7 times? So this is saying, right, A to E, essentially represents pigeons, right? So there are 5 pigeonholes here, right? Yeah. So in this case, n is 5 in the formula. Now, what is the smallest number of students required to, so basically, with the 5 pigeonholes, I want one of them at least to have 7, which means that, right, this guy here, it represents the m plus 1 in the formula, right? So let me quickly go back to this, because at least one pigeonhole will contain at least m plus 1. So basically, in terms of the layers, right, if I sort of say if m plus 1 is 7, right, the number of layers is 6, right? So basically, if you picture the 5 pigeonholes, right, of A, B, C, D, E, I need to place students into each pigeonhole 6 times, right? There's a layer of 6. So the formula works. If I wanted to find the number of pigeonholes, right, that's really what the question is saying. Then my formula, right, in this here, this is the number of pigeons, right? M plus 1, mn times mn plus 1 pigeons, right? That's the number of pigeons we need to do. In this case, that's the number of students we need. Now, if I got m, I got n, then quite simply, right, it's going to be 6 times 7, right? That's the layers. So it'll be, sorry, 6 times 7. 6 times 5, right? So 6 students per 5 pigeonholes, right? And then 1 extra will get me to say that at least one of those holes has 7. So what's that? 31 students. The answer is B. So let me play that through again. I've got 5 pigeonholes. Now, if I was to do the dots here, if I was to play, if I want one of these to have 7, sorry, let me just, let's fill that up, 7, then if I spread it evenly, right, the last dot there, then basically, right, each of the pigeonholes must have, well, it's going to use complex, must have 6, right, in each at least. That makes 30, and then one more will tip it over to say that at least one of these holes would have 7, right? So in this case, 31 is the answer. Now, I like the thought of if you can identify, right, how many pigeonholes there, that gives me n. If you can identify what's the minimum pigeonhole that they want in each, that's n plus 1, that gives me m. Then my formula, right, quite simply says if you multiply m by n, right, that gives you the layers, and then add an extra 1, that's the minimum that we need. Does that make sense? Let's do another one, right? In this case, let's do one that isn't multiple choice, right? Now, this question from ASCM 2022, when I read this, it was completely misleading when they sort of said to you, there are blue, 16 red, 10 blue, 12 yellow. Use the pigeonhole principle to find the minimum number of balls drawn from the box to ensure 9 balls of the same color. Now, I thought it was a bit misleading because they gave you different colored balls. It actually doesn't matter, right? In this case, right, that is the number of colors and not necessarily the number of each ball is your pigeonhole. So in this case, n equals to 3, right? That's the pigeonholes, right? That's the pigeonholes that we need. Let me spell pigeon. Pigeonholes, right? Yeah, it's not about the 16, 10, and 12 are actually misleading. You don't actually need to use them. It's just the 3 colors. Now, I need to place as many balls as I can into the 3 pigeonholes to ensure that one has 1, 2, 3, 4, 5, 6, 7, 4, 5, 6, 7, 8, 9, right? At least 9. Now, best way to ensure that if I do one less, 8. So what that means is, guys, this 9, once again, right? I like this framework. That's m plus 1 equals to 9, m equals to 8. This is the layers, right? So if I go, the layers is 8, I need to fit them in 3 pigeonholes. Therefore, right, mn plus 1 is saying 8 times 3 plus 1, 25. Yeah, makes sense? So I need at least 25 to ensure that I've spread it so evenly, right, that, let's see if I can do that. No, can't paste one look. So if I go 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Right, that's 24. And then the extra one, which makes it 25, would ensure that at least one of those has 9. Now, once again, to be clear, this question is 16, 10, and 12, completely misleading. It's just a number of red, blue, and yellow balls, which make up the 3 pigeonholes. So guys, 25 is the answer. Hope that's okay. Yeah. So another one. Now, a classic question, right? Where show that 100 unique numbers are in the set, that at least 17 of them have the same remainder when divided by 6, right? So once again, what are we saying here? When divided by 6, that is, oh, sorry, take a step back. This is a show question, right? So this one here, they gave you the pigeons, right? They gave you 100 to work with. So this here is the number of pigeons. I need to derive a number that either is less than 100 or equal to 100, right? So let's see. So divide by 6, guys. When I divide by 6, and we're talking about remainders here, right? That tells me what my pigeonholes are, because for the remainders, right? N equals to 6. So actually, let me do it like this. So what are the remainders, right? If I divide a number by 6, what can the remainders be? It can be 1, 2, 3, 4, 5. And of course, there's a remainder of 0 if it's completely divisible. So in this case, N is 6, which represents the pigeonholes. Yeah. And then like the other questions, right? At least 17 of them have the same remainder, guys. So what that means is that there's 16 layers. So M plus 1 is 17. M equals to 16 are the number of layers, right? That I need to sort of allocate into all the pigeonholes. And by that, I can say, therefore, Mn plus 1, right? That will give me the minimum numbers I need to get at least 17 to have the same remainder, right? So let's see. So 16 times 6 plus 1. Now, if this number is equal to 100, I'm sweet. But even if it's less than 100, then 100 would definitely get me at least 17, right? So what's this? 16 times 6. Guys, don't have a calculator. I think it's 97 all up. Yeah, 97, which is less than 100. So therefore, by pigeonhole principle, right? At least, and then you literally copy and paste the question, at least 17 will have the same remainder. Yeah, alternatively, right? I'm sure the teachers will accept you if you just did 100 divided by 6, right? And that should equal to 17 remainder something, is that right? Sorry, 16, right? Because you get 16 layers and then remainder 4. Those 4 have to go somewhere. So that would therefore conclude what we're saying down here, right? So depends on how your teacher wants you to structure it. A lot of times the division approach is fine, but I like this framework. It's, it works for every case, right? So you can see what I tried to do here. In this case, I did exactly the same thing. Identify pigeonholes, identify the layers, and together they would allow me to find the number of pigeons, right, that I need, 97 in this case. 97 is less than 100, so if I had 100, I got excess. So pigeonhole principle works. Guys, after those 3 questions, hopefully you're starting to get that there is repetition, right? And it is for concepts like this where it's a bit hazy, a bit weird, and repetition of framework is really important. So let's do another one, right? Now, this question, I think the hardest thing about this one is identifying the pigeonholes, right? Let's see. So this question here, I haven't seen it in a past paper yet per se, but it's in textbooks. And actually, there was a Sydney Girls paper. In fact, it was a half yearly. I forgot. I think it was this year, right? Or earlier this year. That looks exactly like this, right? So teachers are thinking about this. So let's have a look. And this concept works for all the geometric ones, where triangles, rectangles, and stuff. So it works like this. So show that if 10 points were drawn. Now, That there, just to be absolutely clear, that is pigeons, right? Because I'm drawing 10 points there, right? In an equilateral triangle with sides that, then at least, well, let's see, at least 2 points, right? So at least 2 points means there's only one layer, right? Will be no more than 1 centimeter, 1 centimeter apart, right? That 1 centimeter apart is actually the thing that inadvertently tells you what your pigeonhole is, right? Yeah, pigeonholes. And I'll explain what I mean, right? Guys, if I drew 10 points, right? In here, oh, that's not very, 10 points. They want to demonstrate that at least 2 points will be no more than 1 centimeter apart. So that there is shorter than 1 centimeter. So tick, right? So what does that mean? Now, the best way to understand why that how to use this 1 centimeter fact is, I'm going to subdivide this triangle because it's equilateral, right? I'm going to subdivide it into equal parts. So because it's 3 centimeters, I'm going to divide each side by 3, right? Because that gives me a distance of 1 centimeter each, right? And then if I sort of connect, right, the lines there and sort of draw myself, right, subdivide into smaller equilateral triangles, right? Now, how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So in this case, there are 9 equilateral triangles. And why are these equilateral triangles important? Because if you think about it, right, within one equilateral triangle, right, because the sides are 1, you cannot be, if I had 2 dots in here, right, anywhere, it has to be smaller than 1 centimeter apart, right? Even at its furthest point, where's the furthest? Here and maybe here, right? Not here because Pythagoras, because that's right angle there, the hypotenuse is long. So between that two, that's 1 centimeter, right? So even if the dots occur on the corners, they are no more than 1 centimeter apart, and that's perfect, right? So basically, by defining your pigeonholes, and then now it just so happens that there are 9, right? No coincidence. If I'm placing 10, if I place 1 in every sort of triangle right now, then the 10th one has to go somewhere, which then proves by Pigeonhole Principle the statement, right? So what I'm going to do, guys, I go pigeons equals to 10, pigeonholes equals to 9, yeah, and using the first Pigeonhole Principle, right? So therefore, by Pigeonhole Principle, right? At least, yeah, maybe the best way also 9, which are equilateral triangles. I think your teacher will want to say that. Triangles with 1 centimeter sides, right? So let's copy and paste at least 2 points. At least will be, I'm just copying and pasting it, no more than 1 centimeter apart. So guys, in this case, I reckon the majority of the marks, I mean, it's probably going to be 2 marks, but this pink step here is key, right? Identifying that you've subdivided the triangle into 9 equilateral triangles with 1 centimeter gap. That's how you prove it, right? Is that okay, guys? Let's do, I've got 2 more questions prepared. Not too bad. So in this question here, North Sydney girls, let's see what we have here. Oh, I like this one, right? It's not, this one here just needs a bit of thought, right? So let's see. The netball team's record for 2020 was 16 wins and 4 losses. None of their games were drawn. Prove that the team must have won at least 4 games in a row during the season. Now, there's only 4 losses, right? Somewhere scattered along in the season. Prove that at least 4 games in a row must be won, right? So I think the interesting part here is what are the pigeonholes, right? It feels like I've got pigeons, right? So because we're talking about wins, it feels like that these guys here, that's the number of pigeons. Right. So now the way to describe this is if I have over the season, if I have a loss, I've got 4 losses, right? Which basically means that the time or the games before that are like consecutive, right? So what that means is that, you know, for example, I can have like win, 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 etc. Right? Win. So what that means is that by separating the wins by the 4 losses, I have 5 pigeonholes, right? The number of pigeonholes in this case is 5 pigeonholes. Yeah? Because that would represent the number of consecutive wins, right? So what that means is if I have 5 holes to place and I'm placing 16. So for example, I could go 1, 2, 3, 4, 5, right? 6, 7, 8, 9, 10, etc., etc. So 4 games in a row, guys, this is the number of layers plus 1, right? So this is my M plus 1. In this case, M is 3, right? Yeah. So if I said, therefore, Mn plus 1, the minimum number of games I need to have a 4 consecutive game streak, right? Win streak is going to be 3 times, how many N? 3 times 5, right? Plus 1, which, surprise, surprise, exactly 16, right? So therefore, by Pigeonhole Principle, right? At least 4 wins were observed during the season. Does that make sense? Alternatively, right? And I think a lot of teachers are turning to this as well. You just take 16 and divide it by 5, right? What's that give me? 3 remainder 1. And then you can just go from there to there, right? Whatever teachers accepts, right? So if your teacher's happy to do that division type thing where you identify pigeonholes, just divide instead of doing this working out, because I haven't shown you that general formula, perfect. Do whatever your teacher says. But this one here, the hardest thing was getting that the number of pigeonholes in the first place. Guys, I've got one more question, right? Let's have a look at, oh, it's a multiple choice. Cool. Great way to end it. Now, I thought this question was, it was a bit misleading once again, right? I thought when I first attacked it, I just went down the wrong path. Let's have a look. Yeah, maybe you won't. I certainly did. Bulk Appeals 2020. Given N students are to be placed in 4 classrooms, what is the minimum number of students to guarantee that there are at least 2 students born in the same month in each of the 4 classrooms? Now, I had to read that a few times, right? There are N students to be placed in 4 classrooms. What's the minimum number of students? So we're finding pigeons, right? To guarantee that at least 2 students, right? At least 2 students. So that basically, that's my layers plus 1, right? So in this case, M plus 1 is 2. So M is 1. There's only 1 layer, right? Because if I have 1 student per month, then 1 more would tip it over, right? So that's M plus 1 are born in the same month, right? So that tells me born in the same month, that's the number of pigeonholes, right? There are 12 months, right? Sorry, 12 months. Moths. 12 months in a year. Yeah, in each. Now, the 4 classrooms really got me, right? Because I know that for each classroom, right? For each classroom, I need M times N plus 1. I need 13 students, right? If I had 13 students in each classroom, then at least one month would have 2 students with the same birthdays, right? That makes sense. And then in this question, it just basically says there are 4 classrooms, each of them are doing this. So the answer is as simple as taking 13 and then multiplying by 4. That's all they're doing, right? That's all they're doing. So basically the final answer is 52, right? Yeah, so I got myself in a loop between considering the 4 and I was trying to put all the people in the same class. They've separated it. So they're saying in each, and I think that's the key word there, in each of the 4 classrooms. So basically, it's a pigeonhole principle for each classroom. 13 students are required to double up on a month for each one, 52 in total. Guys, how was that? Short little video, pigeonhole principle, a few questions there. Hope the framework makes sense. Do whatever your school teacher tells you. So if your school teacher just wants division, do division. But if they like this framework, use it. The framework's really good with just how to think about things, right? So sometimes, like in the 100 question where they gave you excess, right? The framework that I set gives you 97 exactly, and then you can use the 100 there and use division to help you. All right, guys, if you like that video, give us a like, subscribe to the channel, and I'll see you at the next video. See you later.